Hi, so remember where we stopped last time? We were looking at the discharging circuit, RC circuit, and solving the differential equation, we found that the charge as a function of time is given by a decreasing exponential, by this function here. Qi is the initial charge on the positive plate of the capacitor, and we have an exponential here, where tau here is a constant called the time constant of the circuit, and is equal to R times C. If you give R in ohms and the capacitance in farad and you multiply them together, you get tau in seconds. Okay, so this function looks like this. It's a decreasing exponential. Here, by 100%, we mean it means the fraction of the initial charge. So you start with 100% of the initial charge, Qi. Then after a certain time, you'd be down to 50%, 37%, and so on as a function of time. 37% here of the initial charge occurs at a special time, and we'll see why in a few minutes. But for now, don't worry too much about this graph. You just have a decreasing exponential. Okay, once you have this function here, you can calculate anything about the circuit. For example, you can find the current. Remember that the current, in the case of a discharging capacitor, the current was given by minus the derivative of QC with respect to time. We have this minus sign here, if you remember. Okay, so if we want I of t, we take the derivative of our function here with respect to time and multiply by minus 1. Okay, so when we take a derivative of that with respect to time, Qi is a constant, so you can move Qi in front of the derivative. Then you differentiate the exponential. The derivative of the exponential gives the exponential back, multiplied by the derivative of the exponent, because we're applying the chain rule. So putting all that together, we get this. I of t is minus, this minus sign here comes from here, okay? Minus Qi, the exponential, times the derivative of the exponent, which is minus t over tau. Remember, tau is a constant, so if you differentiate that with respect to time, the variable is t here. The derivative of that with respect to time gives simply minus 1 over tau, okay? Because the derivative of t is just 1. So multiplying everything together, we get this. That's it. That's the current as a function of time in the discharging RC circuit. Of course, we can also rewrite that in a different way by using the fact that tau is just R times C. So we could write it this way. So again, I of t would be a decreasing exponential, same form as for the charge. And again here, when you set t equals 0 in that equation, if you set t equals 0 here, you get e to the minus 0. So this is just 1. So at t equals 0, the current is equal to this factor here in front. This is the current to start with at t equals 0. So we can call that I initial, the initial current. If we do that, we can write the equation in this form. I of t is the initial current, I sub I, times the exponential, where the initial current is given by Qi over RC. And that's it. That's the current in a discharging RC circuit. Okay? But that's the current, but we can also calculate anything else, including the voltages across the capacitor and the resistor. So if we do that, well, the voltage across the capacitor, the absolute value to be precise, is given by this equation. And that's always true at any time for a capacitor. The absolute value of the voltage across the capacitor is the charge on the positive plate at that time divided by the capacitance. Now, QC of t we know is Qi times the exponential. So I plug that in and I get this. So this equation gives us the voltage, the absolute value of the voltage across the capacitor at any time. Again, it's a decreasing exponential. It goes down with time, tending towards 0 as t goes to infinity. What about the voltage across the resistor? For the resistor, you just use Ohm's law. The voltage across the resistor in absolute value is just R times the current. But we just found the current. So if you do that, the absolute value of the voltage across the resistor is R times the current. You plug in the current we just found, which was Qi over RC times exponential, and you get this. Now, this is not a typo. You look at this function here for the voltage across the capacitor, and this function here for the absolute value of the voltage across the resistor, and they are identical. This is special. It should be that way. This is correct. Because after all, remember what the circuit was. The circuit we were looking at was you had just a resistor, and the capacitor, and then the switch that we close, let's say at equals 0. So you have your capacitor here, and then we add the switch and we close the switch at equals 0. But once you close the switch, there's only the capacitor and the resistor. Therefore, because there's only two things in the circuit, the voltage here and here, between here and here, is the same as the voltage between here and here. They are exactly equal because they're just connected right one to the other one. So the voltage between those 2 points here is the same as the voltage across here, and we see that from our equation. We get exactly the same form for the two voltages. So that's correct. Okay, it's not a mistake that we get the same answer. Okay, now that we have all the equations, we can ask questions. We can start solving problems. For example, if you wait a time equal to one time constant, remember tau is RC and it's a value in seconds. So for a given R and C, maybe tau might be, I don't know, let's say 20 seconds. If you wait for a time equal to the time constant, how much charge is left on the capacitor? And of course here, I want the answer not as a number, but as a fraction of Q initial. So in other words, what fraction of the initial charge is still there after one time constant? Okay, that's a question we can try to answer again, and the answer must be in the form of a fraction of Q initial. Now, the key point in solving a question like this here is to turn that statement into an equation. Okay, at this stage, you could stop the video and try to figure it out. But I'll give the answer now. So what is the charge left on the capacitor after one time constant? In equation, that means the following statement. We're looking for the value of QC of t when time is equal to the time constant. Okay, so this is the time and this is the time constant. So we want the value of this thing here, QC of t, when t is equal to tau. Okay, so what we're looking for is QC of t when we set t equal to tau. But we know the function for QC of t. QC of t is given by this. So we want the value of what is this equal to when you set t equal to tau. And the answer is simply when t is equal to tau, we get QC is equal to QI e to the minus tau over tau, right? So QI times e to the minus tau over tau. All I did was to replace t by tau. And that's our answer. But we want to give the answer as a fraction of QI. Now, notice that this is just e to the minus 1, right? So the answer is QI times e to the minus 1. E to the minus 1 is a number smaller than 1. We should have a number smaller than 1 here because we know we get just a fraction of QI left after a certain time. And you just plug that in your calculator, calculate on your calculator e to the minus 1, and you'll find that this is about 0.368 QI. So about 36.8% of the initial charge is left after one time constant. So for a given circuit, if you calculate the time constant, you know that if you wait a time equal to one time constant, the charge left on the plate of the capacitor is about 36.8 or about 37% of the initial charge. Okay, so that's why the 37% was shown in the previous graph, because this is the percentage you have left when you've waited a time equal to one time constant. Okay, so after one time constant, you have about 37% of the initial charge left, and then you can calculate at any other time. For example, if you wait at twice the time constant. So after one time constant, you're down to 36.8%. You wait an additional time constant. How much charge would be left then? Well, you use the equation, it would be, you set t equal to tau in the equation, and you'll find that, and check that, you should check that, you find that what is left is equal to QI e to the minus 2, because you really have e to the minus 2 tau over tau, and the tau cancel out. So you get QI times e to the minus 2, and if you calculate that, that's about 13.5% of the initial charge. So after one time constant, you have 36.8% left. After two time constant, you have about 13.5% left. So it's going down very quickly. And it's now, as expected, it's a decreasing exponential. If you look, let's say after 3 time constant, you have only left qi times e to the minus 3, and that's less than 5% of the initial charge. And you could calculate like that for 4, 5, 6, and any number of time constants you want. So it goes down exponentially. Okay, we can ask a different type of question. Okay, that's a different, really a different type of question. Now we ask, how long does it take for the charge to drop to half of its initial value? Okay, so again, we have to turn that into a mathematical problem, a mathematical statement. At this point, you could stop the video again and try to see if you can come out with the equation, but I'll show you how to do that now. So what's the statement that we're trying to solve? What's the equation? What we're trying to find is, we're trying to find a time. So we're looking for a time such that the charge is equal to half of the initial value. So in mathematically speaking, we want to find at what time do we have the following equation valid? At what time is it true that QC at that time is equal to half of the initial charge? That's it. This is an equation now. We've turned the question, the statement, into a mathematical equation. So what we're trying to do now is to solve for the t. At what time is this equation true? So how do we do that? Well, QC of t, we know, we have the function for that. So we just replace QC of t by our equation we had before, and we'll solve for the time t. By the way, here, because again, I don't have numerical values, how long does it take? My final answer will not be a time in seconds, because it depends on the resistance and the capacitance. But we can only give the answer as a multiple of the time constant tau. So in other words, what I'm looking for is, after how many tau do we have the charge left on the plate equal to half of the initial value? Okay. So, okay, I replace QC of t by my function, so this is it. That's the equation we have to solve. What are we looking for? We're looking for t. What's the value of t as a multiple of tau, such that this equation here is valid? So I'm solving for t. Well, clearly here, you have qi appears on both sides, so you can get rid of that. And you're left with e to the minus t over tau equal to 1/2. To get rid of the e, you take ln on both sides. Okay, so I rewrote it here okay, so first I've canceled the 2qi, I have this now. E to the minus t over tau must be equal to 1/2. Now, to get rid of the e, I take the ln. I take ln of this side, I get minus t over tau. And I take ln of this side, I get ln of 1/2. So that's it. I get this equation here, and I solve for t. Finally, t is minus ln of 1/2 times tau. That's our final answer. And if you plug that in your calculator, this is approximately 0.693 tau. So at about 0.69 tau, the charge has dropped to half of the initial charge. Okay. We expected that it will take less than 1 tau to drop to 50%, because remember, if you wait a time equal to 1 tau, the charge has dropped to about 37% of the initial charge. So if you want to have 50%, you wait a bit less than 1 tau. So at that time here, the charge left on the plate would be equal to half the initial charge. Okay, so that's our answer. Okay. I ask a different question, but based on the same principle here. Okay, now what about this question? At what time, again, we'll find the time as a multiple of tau. At what time, after how many tau, is the charge left on the plate equal to only 0.1% of the initial value? Okay, now you should be able to solve that. Again, I'm looking for an answer as a multiple of tau. So I'm not looking for an answer as a number in seconds, but as a multiple of tau. So at what time, as a multiple of tau, is the charge left on the plate equal to 0.1%? So we have to set up an equation. So mathematically, what are we trying to find? We're trying to find at what time we have the following equation valid. And right now, you should be able to pause and solve it by yourself, but here's the solution. At what time do we have that QC is equal to 0.1%, which is 1 times 10 minus 4 times the initial charge? So that's what we're trying to solve. Well, we're trying to solve for t that satisfies that. What do I do next? I go back to my function for QC of t. So I have QC of t is Qi e to minus t over tau. I want that to be equal to this. Again, Qi cancels out. Then to get the t, I take ln on both sides and I solve for t. And the final answer is t will be equal to minus ln of 1 times 10 minus 4 times tau. And if you calculate that with your calculator, you get about 9.21 tau. So if you wait a time equal to about 9.21 times the time constant, the charge left on the plate would be less than 0.1%. At that point, mathematically, you have to wait an infinite amount of time for the charge to go to zero. But in practice, in the lab, for example, when you've reached 9 time constant, you can basically approximate the charge left to be zero. So we can consider the capacitor to be fully discharged. We say it's fully discharged when the charge is completely gone. Mathematically, it's not really there yet. It will take really an infinite amount of time. But for all practical purposes, you can treat the capacitor to be fully discharged after 9 time constant. It's basically charge left is basically zero, the current is basically zero, and the voltage across the capacitor and the resistor are both zero after a 9 time constant. Okay, thank you.